Hello. Welcome to RF Aspects of Magnetic Resonance Imaging with Robert Caverly. I'm Mike Hamilton, your host for this IEEE Microwave Theory and Technique Society webcast, which is sponsored by our Education Committee. Before we start, I'll mention a few housekeeping items. First, this presentation will be archived. A recording should be posted approximately 24 hours after we finish the presentation. We'll send all registrants an email when the archived webinar goes up so that you can revisit it or share it with your colleagues. Second, we encourage questions. We'll answer them after the talk, but you can submit them at any time during the discussion. Enter your question in the Q&A box on the left side of the webcast window, and don't forget to click Submit. Third, some words about the interface. You can enlarge the slides by clicking on the rectangle at the top right of the slide area. You can also go into full screen mode if you desire. Refresh or reload the current page if you encounter problems. If you're listening over your computer speakers, you may need to adjust the media player volume or your system's master volume. The icons at the bottom of the webinar window include a resource list. Clicking that link will start the process to download copies of the slides that will be presented today. Now let's introduce our speaker. Professor Robert Caverly received his PhD degree in electrical engineering from the Johns Hopkins University in Baltimore, Maryland in 1983. He has been a faculty member at Villanova University in the Department of Electrical and Computer Engineering since 1997 and is a full professor. Previously, he was a professor for more than 14 years at the University of Massachusetts in Dartmouth. Dr. Caverly's research interests are focused on the characterization of semiconductor devices such as PIN diodes and FETs in the microwave and RF control environment. He has published more than 100 journal and conference papers and is the author of the books Microwave and RF Semiconductor Controlled Device Modeling and CMOS RFIC Design Principles, both from Artec House. An IEEE Fellow, Dr. Caverly is an associate editor of the IEEE Microwave Magazine and a member of the HF VHF UHF Technology, or TC17, and Biomedical Applications, or TC10, technical committees of the MTT Society. So now it's my pleasure to turn the virtual podium over to Professor Robert Caverly for RF Aspects of Magnetic Resonance Imaging. Robert?
Thank you very much, Dr. Hamilton, and good afternoon, everyone. I would first like to acknowledge before we begin Dr. Hamilton and the webinar team for the training to do this presentation for you today, and also Dr. Ramesh Gupta from the MTT Education Committee for inviting me to do this talk, and also a couple of collaborators I've been doing work with over the last couple of years, Bill Doherty, who since retired from Microsemi Lowell, and Ron Watkins, who's currently with the Department of Radiology at Stanford University. So if you take a look at the slide, a number of you listening may at one time have had an MRI scan for an injury or other diagnostic reason. The reason that you had that scan was that MRI scans provide very good images with excellent contrast and good resolution, but they use radio waves, radio frequency or RF power at frequencies in the tens to hundreds of megahertz range rather than ionizing radiation such as X-rays and CT scans. Now the image here shows a high field solenoidal magnet that generates a strong static magnetic field that in MRI parlance is called the B0 field. And it's that B0 field that forms the basis for the MR phenomenon. But what's really less clear and actually quite hidden in the image is what's going on behind the nice white clinical looking casing that surrounds the actual magnet itself. This casing hides quite a lot of electronics, very interesting electronics, and some of it is at RF frequencies. So the intent of this webinar is to try to demystify what's going on behind that casing, to see where RF engineering fits into the MRI process, and to also talk about ways where RF engineers can contribute, or have contributed, are contributing, and can further contribute to advancements in the MRI field. I just want to say at this point that it's a very multidisciplinary discipline. I'm only going to be focusing on the RF engineering, but there's many other engineering disciplines, even within the sort of broad EE community, that are involved in this. So the way I'm going to approach this is by using the following agenda. First, I'm going to talk a little bit about the physical origin of MRI. And I'm going to talk about sort of the atomic level, where the RF actually comes into play, and how an image is constructed. And then I'm going to actually go into the RF systems overview of MRI. And then towards the end, I am going to start looking at some specific circuits that will be, that you might recognize, but are also quite interesting and used in the MRI field, and then draw some conclusions. As a matter of fact, throughout the talk, I'm going to actually try to interject where current research is and where future trends might be. So the MRI signal that the RF engineer eventually detects originates essentially from the nucleons of specific atoms. From a quantum mechanical perspective, a study of the single electron proton system, which is really hydrogen, shows that the proton has the property of angular momentum that has the same dimensions as that of, say, an orbiting particle in the macro sense. And so this angular momentum is referred to as spin. So it's not a physical spinning, but since it has the same dimensions, it's often called just spin. And that leads to a magnetic moment associated with each nucleon. So even though the single proton, single electron system you may have seen in school, each nucleon actually has this spin. If you have an odd atomic mass number, you actually have a net spin. If it's an even number, the atomic mass number, the spins sort of cancel each other out. But if you have an odd atomic mass number, you get a net spin or a net magnetic moment associated with that nucleus. Now, if you don't have a magnetic field, those magnetic moments are randomly distributed, and so there's a zero net magnetization, which we call NMV, or the net magnetization vector. But when you place a sample, and that could be a patient, into the strong magnetic field, like we saw in that initial slide, you actually get a splitting into higher and lower energies of those nucleons, with the lower energy ones in a spin-up state and the higher energy ones in the spin-down state, either parallel or anti-parallel to that magnetic field. Now, there's a slight number fewer of the spin-down particles, so that when all of those are added up, you get this net magnetization that is actually in the direction of the B0 field. And if we call those spin-downs in minus and the spin-ups in plus, the ratio there is governed by Boltzmann statistics, where you notice the B field sitting up there in the exponent. Now, if you look at sort of a typical MRI system where B may be, the magnetic field strength may be 1 Tesla, it turns out there may be 1 or 2 parts per million difference between the two. So the net magnetization is really a very small fraction of the overall spins that gives rise to the signal. And the reason why this net magnetization vector, or M, is so important is that's the eventual signal that we're going to be trying to be picking up. So this net magnetization vector is in the direction of B0, but it's not locked in exactly the same direction as B0, but rather there's a torque on that net magnetization vector that instead of being locked in place with B0, it's in the direction of B0, but it precesses around the B0 line. And it precesses around that B0 line in a very specific frequency called the Larmor frequency, which is essentially related to that magnetic field strength B, and then a quantity term, the gyromagnetic ratio. So notice before I said if you want to increase the net magnetization vector, which will eventually increase the signal that we're receiving, you're also increasing the frequency of that precessing net magnetization vector. The gyromagnetic ratio is different for every atomic species. As a matter of fact, MRI has its origins in nuclear magnetic resonance in its spectroscopy characteristics. The most widely imaged species is hydrogen because it's part of water, and water makes up about 2/3 of the human body. But there are other species that can also be imaged that could actually give a little better images compared with various other parts of the body. So, for example, sodium plays a role in the heart and in the cancer tissues. Helium and xenon, for example, can be used to enhance lung imaging and so forth. Each of those have a very specific gyromagnetic ratio and a very characteristic frequency of precession depending on the magnetic field strength. And for hydrogen, that's about 42.5 megahertz per Tesla of applied magnetic field. So if we look at sort of the standard clinical magnets now that are in the 0.5 to, say, 1.5 Tesla range, you're looking at precessions that are in essentially the HF realm. With research being looked at high field magnets in the 7 and 10 Tesla, we're looking at precessions that are getting up into the VHF, in the case of 7 Tesla, 298 megahertz, or 10 Tesla, about 440 megahertz. Now, I talk about that as being in those frequency bands because the next step is a very important part of the MRI where actually the RF engineers come into play, is if we actually take that proton, and by the way, I'm just going to refer to hydrogen for the rest of the talk here. If we hit that proton with an RF field at exactly the Larmor precession frequency, that is 42.5 megahertz per Tesla, two things actually happen. That net magnetization vector, all of the contributions actually become coherent and form a single, or what looks like a single net magnetization vector. So they become coherent, and that net magnetization vector starts to move out of being parallel with B0, that is, it moves out of the longitudinal plane and starts to flip into the transverse plane. And it's still processing. So imagine that red arrow there representing the net magnetization vector coming out of the slide on the right and going into the slide on the left and so forth, and it keeps spinning. Depending on the duration and the power of the RF pulse, you can actually have that net magnetization vector flip into the transverse plane, which would be called a 90-degree flip angle. And again, depending on the duration of the power, you can adjust that flip angle practically anywhere in between. And there are a number of imaging sequences that may play games, if you will, with that flip angle. But from right now, I'm just going to talk about a 90-degree flip angle. So if we flip that net magnetization vector completely into the transverse plane and then put a coil open to the transverse plane, what happens is that net magnetization vector sweeps by because of the precession. You essentially cause, through Faraday's law of induction, dB dt, and you get an electromotive force that is induced in that those coil leads. So you're actually picking up the magnetization associated with the atoms in the body, the nucleons. That EMF is a function, or the magnitude of that EMF is a function of a number of items. One is the actual strength of the net magnetization vector, which you can certainly increase by B0. Are there limitations to that? And that's primarily the cost of the magnet. Magnet starts to be very expensive as you go above several Tesla. Also the RF power, which we sometimes refer to as the B1 field, the magnetic component of the RF power. And then, of course, as the higher frequency, d by dt increases as well. So what we're picking up are essentially, or will be picking up, are signals originating from atoms and nucleons in the human body. So it's a weak signal to begin with, and so one needs detection of the steams down to the thermal noise floor. Now, one of the problems with this, and this is where MRI is similar to the radar problem. There's a lot of similarities where it's not, or should be a lot of reasons where it's not similar, but one of the similarities is you have a strong transmit pulse and this very weak receive pulse, so you obviously can't, at the same frequency, so you can't pick that up you can't pick up while the transmitter's on. So you turn the transmitter off to be able to detect that weak pulse, and then, of course, the system starts to go back to equilibrium. equilibrium and you start to lose the signal over time. And that loss of signal actually occurs from two different processes. T1, where the spins are providing energy back to the lattice, and then T2, which is actually dephasing or losing coherence of the signal. These relaxation times, though, are not instantaneous, and they can actually go out to 1 or 2 seconds. So they are relatively long-lasting. Of course, as time goes on, the signal gets weaker and weaker because the transverse plane portion of the net magnetization vector decreases. So this seems like it could be a problem. However, there's a lot of contrast that can be achieved by looking at signals at different times of their relaxation. In other words, T1 may be, or so if you take, for example, a fatty tissue that might have a lot of atoms providing a strong signal, but since it's more dense, it decays more rapidly than a leaner tissue, you can use that to actually help with the contrast. Now, this is where the patients come in. If you take a patient, place them inside the magnet, put them in that static magnetic field, those net magnetization vectors all point in the same direction and process at the same frequency. If we apply a 90-degree RF pulse, they all flip that 90 degrees, but the problem is the word all. All of them flip, so you really can't differentiate one part of the body from another by doing so. And the next step is where Paul Alteber actually was a winner of the Nobel Prize, was he came up with the idea of using magnetic field gradients. So you still have that strong V0 field, but you have another set of magnets in there, of lower field strength, to actually slightly vary the magnetic field strength as a function of position. So now what you've done is you have encoded position as a frequency. And that was like I said, that just started the whole MRI. And of course, if it's capable of doing it in one dimension, it's capable of doing it in all 3 dimensions. So now those net magnetization vectors are processing at a slightly different frequency as a function of position. They're a little lower than the original Larmor to the left of isocenter and a little higher to the right. So with a combination of that gradient field and then a band-limited RF pulse, those two in combination can cause the net magnetization vectors to flip in only a specific region. And that specific region is called the slice. So by varying the bandwidth and or the gradient slope, you can make that slice as thin or as thick as the radiologist, for example, may require. And of course, if you make it too thin, there's a smaller number of atoms that can provide signal, or if you make it too thick, you sort of lose some resolution. But that allows you to define a location. You can do multiple slices by having multiple band-limited pulses spread throughout that total bandwidth. But the issue there is you start getting complex pulses. Very simple sin x over x, which is eventually going to have to be created. So that's going to put some constraints on the RF electronics. Like I said before, if it works in one dimension, you can certainly do it in the other 2 dimensions. And the other 2 dimensions are encoded using the terms phase and frequency encoding, and we'll see those terms phase and frequency come back a little bit later. If you've had an MRI, you know it seems to take a long time, and that's because it's not like an X-ray or a photograph. The image actually has to be constructed one line at a time in phase and frequency space. So one has to set a very specific phase, do an RF pulse, do a readout over frequency, reset the phase gradients, do another RF pulse, another readout, and so forth. So the image is actually constructed. And this is a very interesting part of MRI that's out of my area of expertise, and that is the image processing that's involved. But if you have, for example, a 1-second pulse repetition rate, which still would let you pick up the image even though it has decayed for quite a while, and you have a 256-line K-space representation, each line you have to fill up 1 RF pulse at a time, That's 256 seconds, or over 4 minutes to obtain that single image. Notice we're doing phase and frequency, and we're also looking at the amplitude. So the system has to have very good phase, frequency, and amplitude stability at RF to make sure you keep the images quite sharp. Now, this is a cutaway view, sort of the standard cutaway view of an MRI system. So there's your strong D0 field. You have some extra coils that are sometimes called shim coils. The magnetic field strength has to be homogeneous to better than 1 part per million inside of a small imaging volume in the center of that magnet. So you have some shim coils to help adjust that. You have the gradient coils, and then you have the transmitted receive coils that are actually at the RF frequency, or the very narrow bandwidth around a certain RF frequency. So like I said, in some respects, similar to the radar problem, where you transmit a pulse, excite the nucleons, turn the RF pulse off, look at the re-radiated energy coming back from the atoms. And that's the key difference between MRI and radar. So yes, you do have this time, sort of time delay between transmit and receive. But whereas radar looks at reflected signal and so therefore is wavelength dependent, you're actually looking at a signal coming back from MRI that's actually re-radiated. So even though you may have longer wavelengths, you still get very good resolutions because of that. So like I said, similarities with radar are transmit on, transmit off, receive on. But the operation is completely different. So if we look at the sort of high-level 10,000-meter system equipment layout, I don't know how well it shows up on the slide on your screen, but you'll see a thin sort of pinkish line to the left of the slide, and that usually to the left of that denotes what's going on in the so-called scan room. That's where the magnet is. That's where the patient is. That's where a lot of the electronics are that are near the magnet. And to the right, we have into the equipment room, which just by that name is where a lot of the equipment takes place. So if we have a transmit coil, that excites the spins, and then the receive coils pick up and go to a typical receiver. You have to have some sort of transmit-receive control because in many cases the transmit and receive coils are the same antenna, quote unquote. Then you could go to sort of standard low-noise amplifiers. There may be one receive coil, but the trend now is to what are called phased array coils, where you may have 16, 32, 64, or even 128 receive coils with their associated TR components and the associated low-noise amplifiers. So from the low-noise amplifiers, which are in the scan room, the signals then go to the equipment room, and they're digitized and processed. In the equipment room, also the wave shape is defined and created in which to help the radiologist actually determine what it is they want to look at, and then that goes out to a transmitter. Now, here's the thing that really surprised me when I started getting into MRI, is the RF transmitter can be transmitting multi-kilowatts of power at HF and VHF. So multi-kilowatts of power, pulse of course, but a large amount of power is occurring, and that's being absorbed by the human body. So that is a very interesting aspect of that, because since it's being applied to the human body, the amount of RF dosage always has to be monitored to make sure it does not exceed safe limits. More about that later. So we have these multi-kilowatt transmitters supplying power to the body, and now we're looking at very weak signals coming back from the receiver. So of course we need very good TR switches. Some of the work that's being done now on the receive side is in how do you get the signals from inside the magnet into the equipment room, because traditionally you had maybe 10 meters, 15 meters of coax, and you have the problem with losses, the problem with unwanted pickup of signals, noise, and so forth. So some of the research areas right now are looking at, with miniaturization of electronics, maybe after the LNA, we can maybe put some sort of analog to digital converter or other item, turn it into an optical signal, and use optical fiber to bring the signals out. Or just immediate digitization of the signal. We can bring digital signals out. That helps keep the noise down. There's actually some work that's being done now with wireless communication. That is, after the LNA picks it up, it's then sent digitally outside the magnet to something, to a receiver outside. And then to prevent the need for DC power into the magnet, there's wireless power transfer. So a lot of work being done on the receive side of how to get the signals in. On the transmit side, to carry that kind of power, it's pretty much still standard coax, although there have been some research projects that actually looked at putting high power amplifiers in the magnet. On the transmit side, the pulse width and the bandwidth for a particular scan is actually relatively narrow. That gradient in the RF pulse may be a few hundred kilohertz wide. So on a particular scan, the bandwidth is going to be relatively narrow. However, because of such a wide range of gyromagnetic frequencies, that is, you may want to do a hydrogen scan, and then using the same system, you may want to do a xenon or a helium and so forth, that transmitter, the PA, power amplifier, has to operate over an extremely wide frequency range, but at any one time only a narrow bandwidth. Lots of pulse power, although relatively small CW power. Very low duty cycles, but very rapid rise and fall times. You have to have pretty much stable gain, stable phase, and linear power amplifiers. Because we're talking about phase, frequency, and amplitude as part of the creation of the K-space representation, which gives us the image, and that can potentially take many minutes. That PA, even with those power levels, has to have very, very good stability and phase properties. It also has to be very linear because there are PhD theses on shapes of pulses and pulse sequences. So you want to be able to faithfully reproduce those carefully crafted pulse sequences for slice selection. And that means, of course, you're probably going to have a linear amplifier. And if you look at that sin X over X type shape, it's got a high peak to average power ratio, linear amplification. So these amplifiers have very low efficiency, and some of them actually tend to be water cooled. So there's a lot of requirements on that on the transmitter PA for MRI. One of the sort of classic transmit coils, and by the way, I forgot to mention this, a lot of times these coils can kind of be also described as antennas too. So whereas the microwave engineer thinks of an antenna as a dipole or a Yagi, sometimes that same terminology is used in MR when it's referred to really as an antenna, but it's really a coil. But that's changing with high fields, and I'll talk about that a little later. But if we look at the standard transmit coil, it's based on the so-called birdcage resonator, which is as the kind of name kind of implies, it has rungs associated with it and end rings, and the physical dimension of this so-called birdcage coil or birdcage resonator is a function of the dimensions of that coil. Now remember, this coil, the patient actually has to be inserted inside that coil for the scan to take place. So we are looking at potentially, well, as frequency goes up, the resonator has to shrink in size, and it gets to the point where you no longer have the ability to have homogeneous B1 fields, and the resonator also allowing a person to go inside. So the birdcage pretty much is limited to about 3 Tesla and below. For human imaging, that would be about 128 megahertz. For small animal studies, however, the birdcage is still used up to very high field strengths. For the high field strengths that are being investigated now, alternatives to that birdcage are used. One of which is called the TEM type coil, which is the the top slide there, which is obviously cylindrical or partially cylindrical in nature, and it looks like the birdcage except it does not have the end rings. The TEM is essentially an array of parallel microstrip lines to give you a very homogeneous magnetic field in the center of that cylinder. The nice thing about the TEM coil is that you can individually address each one of those microstrip lines, and you can then adjust amplitude and phase and do what's called B1 shimming to adjust the homogeneity of the field regardless of what's actually inside the magnet. So TEM coils are still being looked at. Because of the cylindrical nature of the bore of the magnet, that actually resembles a cylindrical waveguide. So there's also what are referred to as traveling wave approaches for RF excitation rather than coils or TEM. And a lot of these use patch-type antennas, which is the center structure. These are especially useful for head imaging because, as you can see from the shape of that, you can put that patch antenna in the bore of the magnet and put it in close proximity to the patient's head, and then excite the spins using that. And there's a variety of different traveling wave approaches besides just patch antenna. One that I've seen recently is using a helical resonator, because that also puts a homogeneous B1 magnetic field in the center of the antenna, again providing that excitation. So there's a lot of work being done right now in these transmit coils or transmit antennas for high field MRI, and that's usually defined as 7 Tesla, 298 megahertz and above. We still have, however, to tune and match these structures, because remember, the PA is connecting to them. It wants to see a 50 ohm match. If you put a patient in there, different dielectric loading means the frequency of resonance is going to shift a little bit, so you need to tune it and match it. And since this is going to be used in a setting where that you may not have an RF engineer as the operator, you want to have something that one can just push a button and have tuned. So there's a lot of automated tuning techniques that are being developed to do that tuning and matching. And this is just one example that shows an array of switches denoted by the diodes here, just switching in various capacitor combinations to tune in this case, one of the TEM rungs. Remember, though, that those, for example, TEM rung, those are handling a couple kilowatts of power. And so you want to do this quickly. So those switches have to be high speed. They also have to be high power. And practically the only device that can really handle both those sometimes kind of competing elements are PIN diodes. And very quickly, a PIN diode is, just like the name implies, P-type region, intrinsic region, and N-type. When you forward bias it, the resistance can be made very small with a significant DC current. When you reverse bias it, it becomes essentially capacitive, and you can have a relatively small reactance. So just by changing the bias, you can essentially go from low impedance approximating a short circuit to a high impedance, reactive impedance, denoting as an open circuit. And these are very helpful, like, for example, in TR switches. And here's a couple of examples using a TR switch that could be used for MRI. On the left, you see a microstrip version on top, a hardline version on the bottom, or excuse me, in the middle. And on the bottom, you see a commercial unit using, say, two in this case, quad hybrids in a flat pack configuration with essentially LNAs and diodes. But the way this works is, if you look at the circuit schematic in the bottom right-hand corner, you've got the two quadrature hybrids denoted by C1, the transmission lines, and then half a C2, and then the mirror on that on the other side. And you have the PIN diodes at the junction of the two, plus a third one near the preamp or the LNA. The coil obviously is connected to the MRI coil. VN then is going to be from the transmitter, and the preamp is going to be connected to the LNA. So when those diodes are forward biased, or ideally short circuits, signal coming from VN, that's the PA, goes to the hybrid, splits, and it strikes those diodes and totally reflects, and then goes out to the coil. So from the transmit side, you can see those diodes are bearing the brunt of that multi-kilowatt pulsed signal. When you want to receive the MR signal, you turn all the diodes off, and the signal is now coming from the coil into the quad hybrid, splits, and then recombines at the preamp. That third diode there with the dotted line, like I said, is sort of a cleanup diode, because the diodes at C2, which is at the junction of the quad hybrid, are not ideal. So anything that leaks through that third diode can pick up and clean up before the signal hits the preamp. So that's sort of a look at what's going on the transmit side. On the receive side, as I mentioned before, you can use that very big magnet on receive, but the problem is that TEM coil is looking over a large volume, and so it picks up a lot of noise. It turns out that the signal-to-noise ratio on the receive coil is, as you shrink the diameter of that coil, you improve the signal-to-noise ratio. And the signal-to-noise ratio, then, studies have been done that if you look at the diameter of that receive coil, about that diameter between the radius and the diameter into the patient is where you get the peak signal-to-noise ratio. So depending on what you want to image, you would have coils of various sizes because of the signal originating from various depths. When you have these arrays, you'd like to make sure all these coils are completely decoupled so that you eliminate things like noise picked up on one coupling into another. You want them as independent as possible. If they're placed right next to each other, they will have some mutual inductance. And so you will see maybe a 10 or 15% overlap in a so-called phased array of receive coils, and that overlap minimizes the unwanted coupling between the two. Now, I must mention here, this is sometimes called a phased array. But as RF and microwave engineers, when we think of phased array, we think of antennas with some sort of phase shifters, being able to do beam steering. But that's not this case. It's an array of receive coils. And this is a very good picture of what a head coil looks like that really describes everything I've talked about before. And this came out of an IEEE transactions on medical imaging. This shows a head coil that the outer structure has a TEM-like transmit structure, and the inner structure shows an array of receive coils, and as you can see, that overlapping is quite obvious in that structure. One thing to notice, though, is look at the proximity of all of these structures to each other. Those transmit lines are carrying high power. They're a few centimeters away from receive coils that are used to pick up that power. Both the transmitter and receiver are at the same, or tuned to the same frequency, and the patient's head is inside a centimeter or two away from those coils. So if you have two independent coils and you bring them close together through mutual coupling, they could start interacting with each other. You certainly don't want those receive coils to pick up the RF signal when it transmits. So there's a lot of coil detuning and decoupling on both the transmit and the receive side that has to be done to prevent a number of things from happening. One of which is if you could certainly burn out an LNA, but two if those receive coils can heat up significantly, and if you have the patient in close proximity to those, there actually could be a burn. But fortunately, there have been a number of ways to design these receive coils to, again, use PIN diodes to do this automated detuning. Looking at the time, I'm just going to focus on one of the tuning types. You typically have multiple tuning capacitors on any one coil to prevent any individual coil line from being too long. But if you tap off one of those coils, and this now I'm looking at the far right column of images, if you put a detuning inductor there connected with the coil, and then place either, say in this D1 and T2 or back-to-back PIN diodes, or you have a single diode with a controllable DC bias line, on that top, if you apply an RF pulse and that receive coil starts to pick it up, D1 and D2, those fast PIN diodes, actually start to turn on. They pull that detuning inductor in parallel with coil tuner capacitor C and shift the resonant frequency of that right out of the transmit. When the RF pulse turns off, those don't rectify any longer. They disconnect the detuning inductor, and so you're ready to pick up the very weak MR signal. The bottom circuit shows the same thing, only this time it could be controlled, say, from the equipment. Now, all this time I've been talking about these electronics, LNAs, 10 diodes, quadrature hybrids, and so forth. With miniaturization, those can actually all go inside the board. And that makes sense because you'd like to be able to at least get your high gain LNAs as close to the antenna/coil as possible. The problem is most commercial elements use packaging materials that are have ferromagnetic properties. They're made out of nickel, and they are magnetic in properties. So unfortunately, those elements retain magnetism and can distort the image or create unwanted image artifacts. So inside the board, you can't keep commercial electronics. So if you look at various vendors for MR, they will have specific packaging for MR components to eliminate or at least try to reduce the magnetic capability or the magnetic moment of the packages themselves. So fewer parts, they may be more expensive, but they could actually be electrically the same. Magnetically, they may not be. Some of the other research trends, there's a lot of CAD modeling being done right now, especially with high field, but always with high power. You want to have very homogeneous fields. As you go higher in frequency, you actually start seeing wave effects. That is, the electromagnetic field, RF magnetic field, is not homogeneous throughout and actually displays wave behavior where we have intensity in some locations and very weak RF signals in the other. You have to look at the SAR, the specific absorption rate. How much power is being absorbed by the human body and during the RF pulse and over the scan, and does it exceed safe limits? I talked about it before. There's ways being looked at on the receive side to try to get that signal out and minimize cabling. I talked a little bit about component studies, such as for PIN diodes. There's a lot of work being done on there. And novel transmit structures. I talked about the traveling wave type. There's people using metamaterials for various TEM-like structures. And actually on the receive and transmit site, you're actually seeing dipole-like or Yagi-like antennas rather than the traditional coils. So in conclusion, the sort of clinical low-field scanners that you see in clinics right now are very much coil-based, and they have very many coils. Although on the high-field research structures, you're beginning to see sort of conventional antennas. I hope over the last 40 minutes or so you begin to appreciate how necessary a part RF engineering is in the MR system. It's similar to radar, where you've got large and high transmit powers but very weak receive signals. but it's not like radar because it's not wavelength dependent like radar reflection. So another similarity, a signal-to-noise ratio is very important. PIN diodes, which is something I've been studying over many years, are used throughout. They're used for TR switching. They're used for, on the receive side, for patient protection, detuning, decoupling, a host of activities. Further information can be found about MRI. There's quite a few IEEE publications. There was a couple of articles in the IEEE magazine, the dates listed that focused on MRI. But recently in conferences such as IMS or IMBioC from the MTT Society and the EMBS Society, lots of work being done in MRI, very good resources. There is a Society for Magnetic Resonance in Medicine, ISMRM. That is a very interesting society where you have, and see truly the multidisciplinary nature. It's a conference for physicians, for radiologists, for RF engineers, physicists, chemists, very interdisciplinary. Plus there's a number of web links that have much more detail on some of the topics I've talked about. So thank you for your attention, and I'd like to turn it back to Dr. Hamilton, and I believe he will sort of moderate whatever questions we may have.
Yes, that's great. Thank you very much, Dr. Keverly. That was a very informative talk. So now it is time for our question and answer session. Before we start, though, I want to remind you that you can still submit questions through the Q&A panel, and we'll be covering questions here for just a few more minutes. Okay, so one question we have here is with regards to, I think, the data transformation, so or wireless power transfer research activities. What are the challenges associated with those?
That is something that I know about, but with wireless power transfer, there's the amount of energy you can actually get into the system because of the large standoff distance between the energizer and actually the circuit inside. Those are the main challenges, is how do you get enough energy in there to do that. It doesn't obviously have to happen on the transmit side, but it does happen on the receive side. And so that's the challenge with wireless power transfer. At least that's what I have read about.
Okay, that sounds great. Here's a question. Are there any recent reports on effects and perhaps impact of performance based on medical implants such as stents and things of that nature?
There's a lot of work being done on that. There are some implants, from my understanding, that can be considered MR safe. There are some that are conditionally MR safe and some that are completely non-safe. There has been some work done on looking at ways to shim or adjust the RF field away from the implant. I don't know how successful those are because I haven't looked at it, but I do know that there is work being done, but there are some that are safe and some that are completely not safe and others that are maybe safe depending on the scan itself.
So the data is out there? There are reports?
Yes, there is work out there, yes.
Yeah, great. Okay, here's a question about RF shimming. So if you, just wondering if you could make more comments about that. How does the RF power change when RF shimming is used?
The amplitude and phase of the signal, because this is the signal's being originated from the control room, and so each line of the RF signal will be controlled, and it can be controlled amplitude and phase, and so that can be adjusted to provide that homogeneity.
All right, reading through here, we've got a handful more of questions that have rolled in here. Any investigation of GaN switches, gallium nitride?
Actually, yes. And as a matter of fact, that's something that I've been looking at too. In those receiver protection circuits or coil protection circuits, for example, where I have PIN diodes. PIN diodes are well known to be able to handle the high powers. GaN has been actually investigated for that as well, with similar kind of structures. That is, turning the device on and off to maybe pull in a detuning coil to shift. So yes, there has been some recent work done by GaN with GaN switches. I believe it's from Stanford. They've actually done some work with that, actually.
Okay, that's great.
Yeah, there's a recent paper. Yeah, there's a recent paper in the, I believe it's in the MTT Transactions on that within the last couple of years.
Great, yeah, certainly a very interesting material right now. Okay, let's see. This is a question about linearity. So since the PA is very linear, is the PIN diode linearity also an issue?
Yes. Yeah, well, the PIN diode linearity, since it is part of the transmit path, always has to be considered. With PI, since these are in the forward bias direction, it turns out that the linearity of PIN diodes improves with essentially two factors. One is, as the frequency goes higher, their linearity improves. This is just the sort of the native PIN diode. The linearity improves, and it can improve by increasing that DC bias that makes the resistance lower. As a matter of fact, for PIN diodes, there's a linearity metric of QF over R, where Q is the stored charge, which is essentially the DC, related to the DC current. QF over R, F is the frequency, and R is the resistance. And if you have a larger QF over R, you can make the diode more linear. So yes, that always has to be looked at because like the implication in the question is in the RF path.
Okay, here we have another PA question. So I'm going to rephrase this question a little bit. So for the PAs, is there a single combined output that gets split to the coils, or are there many outputs going to separate coils?
I know the one or a couple of commercial designs that I have seen are actually multi-channel. So you would have a rack, in the case of the 16-channel, say TEM, you'd have 16 2-kilowatt power amplifiers, giving you a total of 32 kilowatts of RF power. So those are actually from individual, at least the ones I've seen are from individual PAs. And they're not small. These are rack mounted.
Okay. And thanks to the audience too. You're really rolling in the questions here. So hopefully we'll get everything answered for you. Let's see. Here's one from a safety perspective, I think. So are there ways to reduce the RF absorption on the patient? What are the kind of real safety concerns from your perspective on this?
Okay, so safety is not my area of expertise. I do know, however, that there are different SAR limits for different parts of the body. For example, the extremities can possibly be a little bit higher absorption than, say, the core or the brain for head imaging. So those, so there's a little bit difference there. But that's a very important factor, especially as one goes to higher fields, because the conductivity of the body increases with frequency. Therefore, there's more actual potential for heating of the body, and the RF energy goes to heat rather than to flip to spins. So that's where a lot of CAD modeling is going to come in, is how does the body, how can you minimize that by RF dose or adjusting the field away from particular areas that look like they may be getting heated. Hope that answers the question. Let me just say that SAR and heating is still a huge area of research right now. And those are some of the high-level answers.
And I think that's fine for now. I completely agree. Very important area of research. Okay, so let's see. Here's a question about the switches. So are MEMS switches being used to replace PIN diodes? Is there any current research on this?
I don't know of any. The issue with MEMS is going to be the power handling capability. And so I haven't seen any, especially in the RF path. I believe there's a usage of MEMS in sort of lower signal paths, but in the RF paths, they just don't have the same power handling capability as PINs, or as a previous questioner mentioned, sort of people looking at GaN now.
Right, okay. Okay, and let's see, back to a question about RF shimming. So why is RF shimming used? Is it just to adjust the homogeneity of the fields, or are there other applications? Application on that?
Yeah, there is the homogeneity. It has to be very good, 1 part in a million. Also, that one I do know. It possibly, I'm not. That's the one I know. I don't want to go beyond that.
Okay, that's totally fine.
Yeah, that's getting out of kind of what my area I've looked at.
Sure. Okay. Well, I think that's. Well, maybe one more real quick question. So, question here that just says cryogenic LNAs. So we know these are superconducting magnets. Does it make sense to use cryogenic LNAs for anything?
Well, right now, if you think about the frequency range we were talking about, tens to hundreds of megahertz, commercial LNAs are going to be, have a couple of tenths of a dB noise figure. And that's very good. The noise is coming from a combination of the coil, because it does have some resistance, and so there's going to be some noise, but it's also coming from the patient. And right now, that's why, for example, one may not use multiple coil switches because, not switches, coils, multiple turn coils, is because with every turn of the coil, you start increasing the resistance. So for the noise, there's actually 2 sources, that of the coil and that from the human body. Right now, most of the noise we're looking at is from the human body, which is 40 Kelvin. So cryogenic LNAs, you may get a few tenths of a dB noise figure with those, but right now the few tenths that you get from commercial seems to be sufficient.
Makes sense. Okay, great. So, ladies and gentlemen, I'm afraid we are out of time. There are still a few questions here in the queue, and the presenter will follow up with you with these unanswered questions offline. So as we said earlier, this session will be archived on the Society website at mtt.org. All registrants will get an email reminder with the website address when it's available. For attendees that would like to receive PDH credits, please follow the link in the webcast view and use the code that's provided on the currently displayed slide. Once again, I'd like to thank Professor Caverly for an excellent presentation, very informative, very much appreciate that. And a special thanks to our audience for joining us today. We hope you found today's event valuable and that you'll return for future IEEE Microwave Theory and Technique Society webcasts. Thank you and have a good day.